Welcome to class. In the last video, we took a look at a lot of vocabulary and notation stuff that's going to be important to understand how to follow along in this video. So if you haven't seen that one, go start there. Otherwise, we get to talk about the principle of superposition today, which is a really fun and important result. One last quick piece of vocabulary before we move on to the good stuff. An nth order linear ODE, Ly equals g of x, is homogeneous if g of x is equal to 0. So in other words, if I have some linear ODE, as long as the right-hand side is 0, we call that homogeneous. Otherwise, it's non-homogeneous. Go figure. In the event I have a non-homogeneous equation, we call its complementary equation the version of that problem I would get if I just wrote 0 instead of the right-hand side. So to take a quick look at an example, if I had dy dx plus x squared y equals 0, this is a linear first-order differential equation. It is homogeneous because the right-hand side is equal to 0. But I could fix that very quickly. If I wrote dy dx plus x squared y equals e to the x, now it's non-homogeneous, because the right-hand side, in fact, is never equal to 0. However, we would say that this guy is the complement or complementary equation to this guy. The principle of superposition is a very important result that tells us if I have multiple solutions, say I've found some, if I have multiple solutions to a homogeneous linear differential equation, Lu equals 0, where L is some homogeneous linear differential operator, then any linear combination of those solutions also turns out to be a solution. And by linear combination here, I just mean adding them up. Maybe I multiply them by some numbers, but take a weighted sum of all of them, I still get a solution. Another thing to keep in mind, the c's are allowed to be 0. They're allowed to be anything. So you can add the first couple up. You can add the first and last together. You can take 2 times the third minus 4 times the fifth. And those are all still solutions to the differential equation you started with. And I'm going to prove this for the case I have 2 solutions. It's pretty straightforward from here to do induction on the larger number of solutions, and I encourage you to try that if you know induction. Otherwise, I think showing the case that we have 2 solutions is enough to get the point across here, why it works. So if y1 and y2 are solutions, then what that means is they satisfy my differential equation, right? When I plug in y1, I get 0, and when I plug in y2, I get 0. And let me make this as clear as I can. Right? We're plugging in y1 and y2 to the differential equation. We get 0 in both cases. So now, if I take a linear combination of them, remember that can be any number times y1 plus any number times y2. Notice I have not specified anything about the values of those constants. But if I take this guy and I hand it my differential operator, let's watch what happens. Well, the most important part immediately is that it's linear, so I can reduce this quite a bit. I can split it over the addition and pull out the constants. By the linearity. And now, because it's homogeneous, well, and y1 and y2 are solutions, I know that each of these guys are 0. So what do I get? I get 0. Now at first that might feel bad, but that's actually what we want to show here. Notice we showed when we plug in the linear combination to my differential equation, I get the right-hand side. It satisfies that equation. So, by definition, c1y1 plus c2y2 is a solution. And you can imagine that the case I have more than just two solutions follows a really similar argument.